Hello, my name is Alberto Marquez. In this video we will discuss system dynamics, modelation, and simulation, how actually the software computes its values. First, let's talk about the modeling aspect. The modeling is an iterative process in which we have a problem articulation, that is the definition of the problem, the scope, and which are the questions that we need to solve. From there, we create a dynamic hypothesis. We begin to specify which are the cause effects, and we build our cause effect diagrams. Then we create a formulation. We translate our dynamic hypothesis into the actual construction of the model into typically a software, and we test that model in the computer to see if it's doing what we expect to be doing and what should be doing, and if we have really captured the interesting aspects of what we're trying to discover or the most important variables. And based on that, we define policies and formulation and evaluation of our alternatives that will modify the problem formulation with new questions and new goals, and we repeat the process. In a larger context, the real world will give us information about how to model the system, and that information modifies the system and modifies our own interpretation of the world. We have an interpretation of the world that is both based on the reality that we're experiencing, and if we properly define this model, we will learn more from what we think the reality is, because we keep changing and updating our understanding of the system. We then propose and implement the strategy and structure and decision rules both into the model, and we try to implement those also in decisions for the reality, for the real world. And the benefit of the system is that we can test them to see what we expect to see to happen. Therefore, our decisions for the organization could be more sound. Now, from the perspective of the computations that the system does, the system works with the concepts associated with calculus, whether if it's integration or differentiation. Here at the left, we have at the top the net rate, and the integral of the net rate is the area under the curve. Without getting into very sophisticated mathematics, let's just understand this in a graphical way. The area under the curve represents the integral, and when we represent that area under the curve, what we have is the function that it's underneath, and actually is the change in stock. So it is exactly the same number, literally, when we consider the aggregation of little spaces that represent the area under the net rate, and we measure the growth in the stock. The differentiation is the opposite process. The differentiation of the stock represents the slope of the stock, depicted here with the triangles, and those slopes have exactly the same value as the net rate, and those are the representations . That is a representation for the area and for the slopes as represented here. To be more precise and to understand a little better, the equations that we have in benzene, for instance, for a stock, as the original value of the stock plus the rate times the differential of time. So here, as we see, the analysis, the dimensional analysis, shows how when we multiply the units over time of the rate times at time, it all balances in units. And dynamically, what the system does is that it keeps advancing the clock by little increments, and with this little increment, an update into the value of the stock happens. The computer keeps calculating the area of the rate times dt, which is these little rectangles that you see, and as they keep growing, they keep adding, and as they add, it keeps the balance integrated into the stock. And this is how the computer does an approximation. Now you can see that there are little triangles of gap between the actual function and the rectangle that it builds, and that is a natural consequence of this, of the size of the dt that you select. The larger the dt you select, the more error you will have. In order to reduce the error, you would have to reduce dt, and that's how the computations are done. Now, regarding formulating the rate equations, we need to work a little closer into how to do this. When we were discussing the stock flows, these stocks are pretty much defined always as the integral of the rates. And that is mandatory because that's how the flow goes into the stocks. However, when we talk about the rates, it's a more challenging process because rates could behave in different forms. So the first one is the fractional increase, and that would be when the rate depends on the value of the stock. And in this particular case, we have inflow rate is equal to the growth rate times the stock. A typical example will be the interest rate times the account balance will be the interest due. And these are consequently the ones that we usually do for purpose of exponential growth. In the case of exponential decline, we have that the rate is associated with the outflow rate, and that depends on how fast we're going to decrease based on the previous value in the stock. In that way, we have it in a similar way as the incremental growth. But there is another way to compute this rate, and that is the stock divided by the average lifetime of the stock. So sometimes it is easier for us to understand what would be the average lifetime of each one of the individuals or the units inside the stock, and sometimes we can understand that rate of outflow out of the stock as a percentage or as a function of a decrease rate. And the typical example would be death rate of people is the death rate percentage times the population. That is the number of deaths times the percentage of deaths per population. It's will be the death rate. Also, the number of people dead can be specified as the population divided by the average lifetime. So either way, you would get an estimate of the value of the number of people dead. Other type of rates is, for instance, when we want to make an adjustments to get a goal. This would be an input rate into the stock, and we can compute that rate as a discrepancy between the current state and the desired state. So in this notation, we have S star as the desired state and S just the current state. We compute that difference and divide that by the average time to close the gap. How fast can we respond to fix that discrepancy between what we want and where we are? An example of that is when we are hiring, the number of people we will hire will depend on how many people we actually want minus how many people we currently have in labor, and divide that by how long it takes for us to get new people. And that way we can estimate a net hiring rate. Another rate that we can use or we can represent is a flow that depends on the amount of resources. An example would be that the rate will depend on the value of the stock, labor, and maybe information average productivity. We can increase the production as a function of the labor, and if we want to produce more, we can increase labor. Or of course, we can increase the value of the information. So this would be yet another formulation. For more information, feel free to look in the book Business Dynamics, System Thinking and Modeling for a Complex World by Stedman. This is a great book. It is of high complexity, but if you want to learn more, please look for the content of this book.